So now we're exploring key cybersecurity vulnerabilities that are essential for understanding how systems can be compromised. Let's look at cross-site scripting. Cross-site scripting, or XSS, is a web server security vulnerability that allows attackers to inject client-side scripts into web pages hosted by a web server. This vulnerability often appears in message boards, online forums, and web pages where users can upload data, providing an opportunity for attackers to embed malicious scripts. A cross-site scripting attack occurs when a user's web browser downloads and executes a web page containing injected scripts. Once executed, the script can access sensitive information retained by the browser for that website. This includes session keys, tokens, cookies, or other private data. These malicious scripts are commonly written in JavaScript, a widely used programming language for client-side functionality. The attack unfolds in a specific sequence. First, an attacker identifies a website with a vulnerability that permits the execution of malicious scripts and uploads a harmful script to a web page on that server. Next, the attacker sends an email to a target user containing a link to the infected page. When the user clicks the link and loads the page, their browser runs the malicious code, which then sends the user's private data, such as cookies or session tokens, back to the attacker. So to clarify, XSS indeed enables the injection of client-side scripts into a web server's pages, and the attack happens precisely when a browser executes those scripts. Attackers often use methods like emailing a link to the infected page to trick users into triggering the attack. There are three distinct types of cross-site scripting attacks. First, a reflected cross-site scripting attack, also known as a non-persistent cross-site scripting or reflected XSS. This occurs when an injected script is returned to a client in response to an HTTP request made by that client. This type of attack is activated through a link that sends a request to a website with a vulnerability allowing script execution. Attackers might use tactics like placing shortened URLs on a site that they control, or sending phishing emails to deceive users into clicking the malicious link. Second, a stored cross-site scripting attack, also called persistent cross-site scripting or stored cross-site scripting attack, involves a malicious script being stored in a web server's backend database. This script is then delivered to all clients who request the affected pages, making it self-contained within the web application. Unlike reflected cross-site scripting, it doesn't require the attacker to trick a user into making a specific HTTP request because the harmful content is already embedded. And third, a DOM-based cross-site scripting attack. This takes place entirely within the client's web browser. The Document Object Model, or DOM, is a standard object model and programming interface for HTML that defines how to get, change, add, or delete HTML elements. In a DOM-based XSS attack, malicious code is inserted into DOM objects and executed by the browser without being sent to the web server. Here, an injected script runs in the browser without server involvement, such as when an attacker manipulates the DOM object directly. Now let's look at cross-site and server-side request forgeries. Requests to a web application can be forged to deceive the application into performing unintended actions. There are two main types: cross-site request forgery, or CSRF, and server-side request forgery, or SSRF. A cross-site request forgery attack, also known as client-side request forgery, occurs when an attacker sends a forged request to a web application on behalf of an authenticated user, exploiting the trust that the application places in that user. For example, consider a banking web application that stores an authentication token on a user's device after they log in. If the user doesn't log out, the token may remain active and an attacker could use it to perform a banking transaction without the user's knowledge. The attack proceeds as follows. A user authenticates to the web application, which stores an authentication token on their device. An attacker then sends a forged request, which serves as embedded script or a URL to the user. The user unknowingly forwards this request to the application, including the authentication token with it. Since the request appears to come from an authenticated user, the application can process it, potentially sending the user's confidential data to the attacker. So in a cross-site request forgery, the forged request originates from the user to the web application, not directly from the attacker. And the goal here is to exploit the application's trust by sending the malicious request. This attack is possible because the web application cannot distinguish between legitimate requests and forged ones from an authenticated user, completing all requests from a trusted source without additional checks. In contrast, a server-side request forgery, or SSRF, involves an attacker sending forged requests from an application's server to other servers. This attack tricks the server into making unauthorized requests, allowing the attacker to access or modify internal resources that are protected from external networks. A server-side request forgery can also enable other services available to the server through its loopback interface. For instance, an attacker might send a forged request to a web server to retrieve user account information from a back-end database server. That process works like this. A firewall protects back-end servers, such as a database server, from direct external access. The attacker sends a forged request to the web application, which, to respond, retrieves data from the database server. The database returns the database requested action to the application, which then sends it to the attacker. In server-side request forgery, the target is a back-end server storing protected information, and the forged request is sent to the web server to gain access or modify internal resources. The aim here is to deceive the server into performing unauthorized actions, exploiting its ability to reach otherwise restricted systems. Now let's look at memory vulnerability. Here we'll examine buffer overflows, integer overflows, memory leaks, and pointer dereferencing. A data buffer or buffer is a region of memory used to temporarily store data while it's being transferred between locations, such as holding a user's input to a program. A buffer overflow or buffer overrun is a programming error that occurs when the size of the data to be stored exceeds the buffer's allocated capacity. This causes the excess data to overwrite adjacent memory locations not assigned to the buffer. This issue arises from improper input handling, where a program fails to sufficiently validate user input to ensure that it fits within the buffer's size. If a buffer overflow overwrites executable code, it can lead to incorrect program outputs, memory access errors, or unexpected termination. A buffer overflow happens because the input size is larger than the buffer size. It can be prevented by restricting access to memory locations beyond the buffer's allocated bounds. An integer overflow is another programming error occurring when the result of an integer operation exceeds the maximum size or falls below the minimum size of the integer type used to store it. This type of error can be prevented by checking for overflows after each integer operation where an overflow might happen. A memory leak happens when a program allocates heap memory but fails to deallocate it when it's no longer needed. This results from improper memory management by the programmer. An operating system allocates two types of memory to a program: stack, which stores local variables and is used for static memory allocation managed automatically by the operating system, and heap, which stores global variables and is used for dynamic memory allocation managed by the programmer. Heap memory isn't automatically deallocated, so if a programmer neglects to free it, a memory leak occurs, reducing the computer's available memory and degrading performance. A pointer is a program variable that stores a memory address, referencing a specific location in memory. Pointer dereferencing or object dereferencing is the act of retrieving the value stored at that address. Pointers improve performance because copying and dereferencing them is faster than copying or accessing the data that they point to. However, if a program dereferences a pointer with an invalid address or null value, it can stop functioning correctly and crash. This can potentially leave the system in a state that allows unauthorized access to resources. Error handling, the process of responding to and recovering from such errors, is crucial to manage these conditions. Now let's look at replay attacks and pass the hash attacks. A replay attack, also known as a repeat attack or playback attack, is a network attack where an attacker intercepts a data transmission and maliciously repeats or delays it. In this way, they function as a type of man-in-the-middle attack. For example, if a user sends login credentials to a system and an attacker intercepts them, the attacker can later replay those credentials to authenticate the certificate or data. This is possible because the receiving system doesn't distinguish between identical messages messages received at different times. To prevent this, a sender can append a timestamp or sequence number to each message, allowing the receiver to discard repeats. A session ID is a unique number assigned by a web application to an authenticated user, valid for their session to identify them. A session replay attack uses this ID to impersonate the user for fraudulent transactions or activities. The attack process involves a user sending a transmission to a server and an attacker intercepting it. The attacker then replays it at a later time. It's conducted by replaying a previously intercepted transmission, not random data or user requests. It relies on the server's inability to differentiate message timing. A pass the hash attack targets the new technology LAN manager, or NTLM. The NTLM is a challenge response authentication protocol that uses a domain name, username, and password hash instead of sending the password in plain text. In this attack, an attacker authenticates to a server or service using a user's NTLM password hash, bypassing the need to brute force the hash to reveal the password. This exploits an NTLM vulnerability where the password hash remains static across sessions until the user changes their password. The attack works against any server or service accepting NTLM authentication. It starts with a user sending their domain, username, and hash to NTLM server. An attacker then intercepts this and then uses the hash to authenticate. It's conducted by sending the intercepted domain, username, and hash rather than random hashes or brute force passwords. It is possible because the hash doesn't change session to session, therefore requiring all three components for success. Now let's look at injection attacks. Injection attacks, also called input validation attacks, insert malicious input like codes, scripts, or commands into a program or database query, thereby exploiting inadequate input validation. We'll cover SQL, XML, ADP, and DLL injections next. An SQL injection, or SQLI, targets applications by inserting malicious SQL statements through user input fields, creating a syntactically correct SQL statement when processed. It is widely used against SQL database-driven websites that allow user input. XML injection attacks manipulate XML-based applications. Here, an attacker inserts malicious content into an XML document to alter the application's logic. The attack impacts application logic but not its performance. DLL injections force a process to load and execute malicious code from a DLL, or dynamic link library. A DLL library is a shared library of code and data used for operational dialog functions. It aims to manipulate a process's behavior, such as reading and manipulating a password text box. The attacking process attaches to the victim process via a Windows API call and allocates memory with write access. It stores a malicious DLL's path there at that point. It then creates a remote thread to be executed. DLLs can be used by multiple programs, not just one, and the attack runs malicious code in the victim's address space, not stopping execution but altering it. An LDAP injection targets the Lightweight Directory Access Protocol, or LDAP. This is used for directory services over IP networks and stores usernames and passwords centrally. It exploits apps constructing LDAP statements from user input. This manipulates the LDAP query and allows data viewing or modification, but not server shutdown. It gives the attacker ongoing authenticated access to the system, database, or target directory. Now let's look at race conditions and resource exhaustion. A race condition occurs when multiple concurrently executing processes access a shared resource like a file, memory location, or variable at the same time. This then affects multi-threaded programs or multi-core CPUs. A resource exhaustion attack or resource starvation attack acts as a denial of service attack. It slows or disables an application by consuming its limited resources like memory, CPU storage, or database connections. A CPU exhaustion attack might use all allocated CPU cycles, reducing responsiveness. It's possible because the app doesn't properly control resource allocation, like a memory leak exhaustion memory, impacting the app and its host operating system. An attack continuously writing to an SSD would exhaust its capacity, potentially causing authorized users a denial of access. Now let's look at driver manipulation. This occurs when a device driver or hardware driver controls computer-connected devices such as keyboards or printers, providing a software interface for the operating system or application. Two driver manipulation methods exist. First, a shim attack or shimming inserts malicious code into the shim. A driver shim is a software library intercepting and modifying driver calls which control the device's applications on the operating system. Shimming adds a layer between driver and the OS, exploiting compatibility needs. Second, a refactoring attack adds malicious code to a driver via refactoring. So it still functions, but it also executes the malicious code. One example is sending print jobs to an attacker's printer instead of a different intended destination. When we talk about privilege escalation, we are talking about an attack that is gaining account privileges beyond those assigned to the user's application access protocol. This enables unauthorized actions like install malware without permission through application vulnerabilities, permission flaws, or operating system configuration errors. Vertical privilege escalation moves from lower to higher privileges, like a user accessing a banking site's administrative functions. Horizontal privilege escalation gains same level privileges, like accessing another user's bank account. In vertical cases, an attacker might use a buffer overflow to gain administration credentials. In horizontal, cross-site scripting might steal session cookies, or a CSRF might trick a user into an action with their own privileges. Social engineering could also yield horizontal access to a user's account. Now let's examine password attacks. A brute force attack is a type of attack where the attacker tries all possible password combinations for one username until it is successful. The brute force attack is most effective against short passwords. So in brute force attacks, the attacker targets one username, attempting passwords systematically. This type of attack is most commonly used with the help of software designed to increase and amplify the output of the attack. Alternatively, we have spraying attacks, where a common or default password is tried across many usernames. If it succeeds, it occurs when one password and username combination matches and is most effective in situations where default passwords have not been changed. Next, let's look at directory traversal, API attacks, and SSL stripping attacks. Directory traversal or path traversal is a web app vulnerability allowing unauthorized access to files outside the root directory. A vulnerable server might expose system file directories, giving access to the host files. Prevention in this case involves restricting server access to the root directory. Next, we have API attacks. An API or application program interface is a set of functions and protocols needed for an application integration. In this case, a web application sends, requests, and receives responses via its API functions. This facilitates communication but also opens up vulnerabilities. API attacks exploit these vulnerability entry points to disrupt services and access data. And finally, SSL stripping or HTTP downgrading is considered a downgrade attack. This type of attack is a man-in-the-middle attack where the attacker intercepts the server's HTTPS redirect to a client HTTP request. Its goal is to shift an HTTPS connection to a different destination and then remove encryption. In this way, the attacker engages in eavesdropping on the user's activity and can view the user's data and information as it is exchanged over the internet.